For decades, computers were completely blind to the real world. Unless a human sat down and typed data into a key punch machine, the digital world had no idea what was happening. That creates a severe speed limit on automation. You cannot rely on human data entry to manage a city's traffic grid in real time, or to constantly monitor the vibration of an industrial turbine right before it fails. It is simply too slow. The Internet of Things, or IoT, solves this by removing the human bottleneck entirely. It creates a state of hyperconnectivity, where everyday physical objects are embedded with sensors and network links to share real-time data directly with each other. By bypassing human input, computers go from being passive calculators sitting on a desk to contextually aware systems that can react to changes in their environment the second they happen. To actually build that bridge between physical reality and digital automation, engineers use a specific structural roadmap known as the IoT stack. This diagram is the four-stage IoT architecture, separating the physical hardware layers at the bottom from digital applications at the top. To understand its mechanics, we will track a single piece of raw data climbing this exact stack from the very bottom. Level 1 is the sensing layer. This is where hardware devices like ultrasonic rangefinders or DHT-11 sensors interact with the physical world, detecting conditions like distance, temperature, or humidity, and translating them into usable electrical signals. Look at the top right of this diagram, showing the internal breakdown of an MQ2 gas sensor. When a target gas hits that sensing element, a chemical reaction changes the internal electrical resistance, converting a physical gas into a measurable voltage drop. Actuators do the exact opposite. Components like LEDs, motors, or automated valves receive an electrical signal and convert it back into physical, mechanical motion. Together, these edge devices form the nervous system of the IoT ecosystem, translating raw reality into voltage, and voltage back into physical action. But raw voltage from a sensor doesn't do anything on its own. It requires localized logic to make sense of the data, which brings us to the processing layer. This table breaks down the two main types of brains. On the left, microcontrollers, or MCUs, integrate the CPU, memory, and pins onto a single low-power chip. On the right, microprocessors require external memory to handle heavier tasks. This schematic displays the Arduino Nano, a quintessential 8-bit 5-volt microcontroller. The central 8-mega 328 chip handles the localized processing, while its layout is specifically designed to be breadboard-friendly for rapidly prototyping those edge layer sensor connections. Compare that to a Raspberry Pi. This is a higher-level system on a chip. It runs a full Linux operating system and manages complex data abstraction and high-bandwidth internet connections, rather than executing simple microsecond-level sensor logic. Matching the correct processing hardware to the specific layer of the stack dictates the entire system's energy efficiency and operational cost. Once the data is processed at the edge, it has to be sent out. Standard internet protocols used for web browsing are simply too heavy and power-hungry for a tiny battery-operated sensor. One solution is MQTT. Instead of a constant draining connection, devices publish tiny data packets to a central broker. That broker routes the information only to specific devices actively subscribed to that data feed, saving massive amounts of bandwidth. This graphic compares the standard networking model with the IETF modified 6-layer model. Engineered for constrained, low-power networks, its top layers rely on lightweight protocols like CoAP. This ensures small data packets reliably reach their destination, even when the network is spotty. But as we connect billions of these new sensors, we run into a hard physical limit. The existing internet infrastructure simply does not have enough unique IP addresses to label every single device. This chart contrasts the older IPv4 standard with IPv6. IPv4 provides a 32-bit address space, maxing out around 4 billion addresses. IPv6 introduces a massive 128-bit address space and automatic configuration, a hard requirement for an ecosystem of this size. Without these highly specialized, lightweight routing protocols and effectively infinite address spaces, a global IoT network would instantly collapse under its own weight. To see how this entire stack operates in practice, we can look at a single millisecond of action involving an autonomous vehicle navigating a city. At the physical layer, LiDAR sensors on the part continuously bounce invisible laser pulses off their surroundings, converting physical distance into raw electrical data. At the logic layer, an onboard microcontroller processes that data instantly, identifying a sudden proximity alert when an object enters its path. Moving up to the network layer, the vehicle immediately transmits a cellular V2X signal to a nearby smart traffic light, triggering an actuator to extend a red light and prevent a collision. That complete chain reaction, from physical detection to logical processing to mechanical action across the grid, happens in a fraction of a second, with absolutely zero human intervention. This macro-scale integration of interconnected hardware, localized logic, and network protocols is what drives Industry 4.0. We started with humans manually typing numbers into machines just to give computers a static snapshot of the world. Now we have self-regulating cyber-physical ecosystems that monitor and react to their own data streams. The Internet of Things moves humanity away from being the manual data gatherers of the world, positioning us instead as the high-level overseers of an automated reality. To explore the hardware specs behind these systems, check out the links in the description.